Welcome back to Logic, Language and Information 2. The task for today's lesson is to give a formal treatment of the syntax and semantics of predicate logic with identity. First, the syntax. Identity is a two-place or binary predicate, so we need two names together with a predicate symbol to put together to form an atomic formula. Identity as a special predicate has different conventions for writing it. We write A is identical to B this way. It's read A is identical to B. We do not write the identity predicate symbol first, followed by the two names, as we would with a regular binary predicate because, well, it looks weird. Identity is most naturally written in infix form, with the identity predicate symbol between the two names. In logic, we do not say A is equal to B because that could mean equal in some respects but not others. Identity assertions express the stronger notion that two names denote exactly the same object. For negated identity assertions, we also use the infix notation. We write the non-identity symbol, that is, identity with a / through it, in between two names and is read as A is not identical to B or A is different from B. This is to be understood as approved shorthand for the formula. It is not the case that A is identical to B. More precisely, the semantics or meaning of the formula, A is not identical to B, will be identical to the semantics of the formula, it is not the case that A is identical to B. Let's review the formation rules for predicate logic and then see how to add on one more clause for identity atomic predicates. If F is an n-ary or n-place predicate symbol, and A1, A2 up to AN are names, then the symbol F followed by A1, A2 up to AN is a formula, and these are atomic formulas of predicate logic. For the propositional connectives, if A and B are formulas, then so are not A, A and B, A or B, A implies B, and A if and only if B. Quantifiers use variables x, y, and so on. These are introduced by substituting all occurrences of a name with a variable, and the result is not a formula because it contains uninterpreted variables. But a well-formed, universally or existentially quantified formula is the result of binding a free variable with a universal or existential quantifier. All good. That's the standard syntax for basic predicate logic. The only extra clause we need to add is, for identity, is the following. If A and B are names, then A is identical to B is a formula. It is a new sort of atomic formula. Remember that the formula A is not identical to B is the approved shorthand for it is not the case that A is identical to B. With this shorthand convention, we do not need to add a separate clause for non-identity. In spite of the obvious temptation coming from elementary mathematics, we do not read A is identical to B as A equals B. If we insert names of people like Alice equals Bob, then the result is grammatical nonsense. In mathematics, the objects are numbers or more general mathematical entities, and identity is equality. But in logic, we work with models whose domains can be any and all sorts of objects in the universe, real or imagined. So we work with identity and non-identity. And identity means equal in all respects, or denoting exactly the same thing. For some examples, let's start with this one. To make the reading a bit more concrete, let's suppose the binary predicate PYX means Y is as poor as X. Then, reading the formula, for all X, there exists Y, there exists Z, PYX and PZX, and Y is not identical to X. What does that mean? It says for every X, there exists Y and Z different from each other, both of whom are as poor as X. More informally, everyone has at least two people as poor as them. Okay, next one a bit trickier. The formula exists Y such that for all X, X equals Y. What does this say? Well, start with the main connective and work away. It says there exists an object Y such that no matter how you choose an X from the domain of the model, X is identical to Y. The only way this can happen is if the model contains exactly one object. Remember that the domain of a model must be non-empty, so it has at least one object. If this formula is true in a model, then the model must contain exactly one object. Okay, now it's your turn. Which one or more of the following sentences express that there is at most one object with property F? Be careful. It means we need either 0 or 1 objects with property F, but definitely not 2 or more objects with property F. So how did you go? The correct answers are B and E. Formula B can be read as saying, if there were 2 objects, X and Y, that both had property F, then they would be the same. This formula is true exactly when there are 0 or 1 objects with property F. The other correct answer is formula E, which says there exists an object Y with the property that if there is anything with property F, then that thing X is identical to Y. So this object Y does not necessarily have property F because there might be nothing with property F. But if Y does have property F, then nothing else different from Y can have property F. So this formula is also true exactly when there are 0 or 1 objects with property F. For the incorrect answers, formula A says, in fact, that everything has property F, whilst formula C says that if names A and B are of objects with property F, then they name the same thing. But formula C does not rule out there being some other different object different from both A and B, say with name C, such that FC is true. So that one doesn't work. Formula D expresses that there is at least one object with property F instead of at most one object with property F. So if you have any remaining questions or queries, first look at the course notes and then go to the discussion boards, and I'll follow the postings there. Next, we'll make precise the semantics of identity added to predicate logic. The extra thing we have to do to interpret identity is exactly nothing. We already have the ingredients within any model to interpret identity. Recall that a model M is a pair consisting of a domain D and an interpretation I of the names and predicates. The atomic formula A is identical to B is true if and in a model M, if and only if the object interpreting name A is identical to the object interpreting name B. They are the same object. Conversely, using our shorthand convention, a negated formula, A is not identical to B, is true in a model M if and only if the object interpreting name A is different from the object interpreting name B. So let's see an example of truth in a model for identity and non-identity formulas. We'll go back to our long-running favourite example of a model whose domain has three objects: Ada Lovelace, Kurt Gödel and Albert Einstein. In this language, we happen to have only two names, A and K, and the model interprets A with Ada Lovelace, little a with Ada Lovelace, and the name little k with Kurt Gödel. We also have a binary predicate, capital A, to place, which means X admires Y. AXY, X admires Y. And the interpretation is as shown in the table. The first row of the table says that Ada Lovelace admires herself but does not admire the other two, which makes sense because she died in 1852, well before the time of Gödel and Einstein. The second row says that Kurt Gödel admires Ada Lovelace and admires Albert Einstein but does not admire himself, which is probably true. Gödel was a very troubled genius with doubts and anxieties. And the last row of the table says that Albert Einstein admires, well, everyone in this model: Ada Lovelace, Kurt Gödel and himself. Okay, let's look at the truth or falsity of some formulas in this model. First, the formula expressing that everyone admires someone else. This is written: for all X, there exists a Y, X admires Y, and X is different from Y. This is a universally quantified formula, so for it to be true in this model, we would have to verify that each of the three instances are true in this model. But the first instance for Ada Lovelace is in fact false. There does not exist anyone different from Ada Lovelace who is admired by Ada Lovelace. So the formula comes out false in this model. Another one, the formula expressing that if you are admired by everyone, then you are Ada Lovelace. Another universally quantified formula, so we have to verify that each of the three instances are true in this model. First, the instance for Ada Lovelace. It is true, looking down the first column of the table interpreting the predicate A. The antecedent of the conditional expands out as a conjunction. Lovelace admires Lovelace, and Gödel admires Lovelace, and Einstein admires Lovelace. And this conjunction is true. Then the consequent of the conditional is Lovelace is identical to A, which is also true. Second, the instance for Kurt Gödel. The antecedent of the conditional here is false because Gödel does not admire himself. Hence, the whole conditional comes out as true. And third, the instance for Albert Einstein. Here, the antecedent of the conditional is also false because Lovelace does not admire Einstein, hence the whole conditional is true. We have all three instances true in the model, so the universally quantified formula is thus true in the model. Okay, this lesson has introduced the formal syntax and semantics for adding identity to predicate logic. In the next lesson, Greg will show how to extend the proof tree method to accommodate identity and difference.